Hey guys, let me know if you have any questions about this Friday's test or anything like that. I have a Kahoot that I made that we can probably try out too if you guys want to do any practice. Yeah, so let me know if you have any questions about the study guide or anything like that. Hope you guys are doing well. Question 8, let me take a look. Okay, yeah, so you have mercury oxide decomposing into liquid mercury and oxygen gas. So you have a solid, for questions like that, where if it gives you an equation and it just says, is the entropy increasing or decreasing, is it positive or negative? You just want to think about whether it's becoming more ordered or more disordered. So originally, the only reactant is a solid, right? It's just solid mercury oxide. So a solid is made of these atoms or molecules in this case, because it's HGO, it's a compound. It's made of these different particles that are fixed in specific locations. I mean, they'll vibrate and they'll shake, but they're not like, traveling from this point to that point because it's a solid, right? So you have this solid mercury oxide, which is, when it comes to the three phases of matter, and their entropy, right? When it comes to entropy increasing, solid definitely has the least entropy because a solid has particles that are in fixed locations. They'll shake and they'll vibrate, but a solid is arranged in a much more orderly way than liquid, for example, right? Because a liquid has an unfixed shape. It takes the shape of whatever's holding it. If it's just on the ground, it'll be a puddle. If it's in a cup, it'll be a cylindrical shape. And gases have the most disorder, the most entropy, because gases don't only have an unfixed shape; they have an unfixed volume too. They expand as much as possible in all directions. So for that problem, it's a solid that's decomposing into liquid and then gas. It's oxygen gas and just liquid mercury. So that would definitely be positive entropy. Right, so that one would definitely be positive S because it's increasing in disorder, right? So the particles in the solid, they're in these fixed locations, they're shaking. There's some slight disorder in a solid, depending on how much they're vibrating and exactly which particles where. But a liquid, for example, is even more disorderly because they can move in so many different locations. They're fluid. A gas is even more disorderly than that because not only does it move around and take the shape of its container, but it can really spread itself out and maximize how much space it takes up three-dimensionally. So yeah, that one definitely be a positive S, positive entropy. So yeah, positive S is more disorder. Negative S is more order. Yeah, let me know if you guys have any other questions or anything like that. Oh, so delta H is enthalpy. H is the letter for enthalpy, which is measured in joules, right? So it gets kind of confusing because we've talked about energy at the beginning of this unit, but we haven't really had a variable for energy itself, right? So energy is measured in joules, right? So energy is measured in joules or calories, but we're really sticking with joules for the most part. And we're talking about different forms of energy. In this unit, we're talking about heat, which is the transfer of energy, right? And then we're talking about enthalpy. And enthalpy just always has that delta sign in front of it. Um, because enthalpy is always based on the difference between the energy from the reactants and the products in a chemical reaction. The most basic definition of enthalpy, which again, enthalpy is measured in joules, just like heat, just like energy. So it's kind of confusing because it's like energy is like the big umbrella term, the very broad term for all of these things, but we haven't really even had a variable for energy itself, which if we did, it'd probably be the letter E. But anyways, we just talked about it conceptually because we're really dealing with these different types of energy. Heat, which is the transfer. Enthalpy is the internal energy of a substance due to what's contained within their bonds, because the chemical bonds that make up a substance hold energy themselves. So when it comes to delta H, change in enthalpy, it's really the enthalpy of the products minus the reactants. So it's really the products minus the reactants, right? So it's the internal energy. Enthalpy is just the internal energy within a substance. For example, like an ice cube, right? Frozen water has some internal energy. There's some enthalpy in there, right? Because there's energy within the bonds that are holding the water molecule together, some energy within the intermolecular forces that are holding each of the water molecules separately themselves all together in this, solid structure. Um, and then if I compare that, if I compare solid ice, solid water to steam, right, water vapor, which is at a much higher temperature. If I have like a container of steam, maybe I'm cooking something, I put a lid on it, so there's like some steam forming inside the pot or whatever. That's much more enthalpy because enthalpy is the internal energy, right? Enthalpy is the internal energy. It's within the substance um, due to the energy within its bonds, as well as due to like things like the velocity that they're moving at, how it's related to things like temperature. If something's at a higher temperature, it's going to likely have more enthalpy. So yeah, it's the internal energy of the substance itself. That's enthalpy. Delta S is something completely different, right? So delta S is entropy. So entropy is S, enthalpy is H, right? So delta S is entropy, and it's actually units joules per Kelvin. So it's not just joules; it's joules per Kelvin for entropy, right? And so entropy is a measure of disorder. So if you have something that is at a much more, for example, going back to water, solid water, like an ice cube, um, when you think about all the possible ways that you can have an ice cube formed, all the possible locations for those water molecules, there's a good amount. But for the most part, as long as it's not melting or anything like that, it's staying in an ice cube, right? Maybe it's in the freezer, for example. It's staying in this cubic structure, right? This solid structure. The molecules are not traveling all over the place. They're just maybe shaking and vibrating a little bit, and that's it. So if you compare an ice cube to steam, right, water vapor, that's something that has way more randomness and disorder to it, because each water molecule that's a gas, in this case a vapor, can be in so many different possible random locations, so many different random possibilities. So if there's more randomness, right, if there's more randomness or just possible outcomes. I'm kind of saying the same thing here, but just saying it in different ways, or disorder, just to see if any of them kind of click. So if there's more randomness or just possible outcomes or disorder in arranging something, that means it's positive entropy, right? So it's positive entropy if there's more just randomness to the situation. So sometimes it's helpful to kind of think about, other examples too, like when it comes to like coins. Let's say I'm trying to get half heads and half tails for some coins, right? So if I have 2 coins, I can have a head next to a tail or a tail then a head, right? So if I'm trying to think about different ways I can have a collection of coins, whether it's 2 coins or whether it's, 50 coins or whatever, if there's only 2 coins, I only have 2 ways of setting them down to have half heads, half tails. I can have a head then a tail or a tail then a head. So that's 2 possible outcomes, right? But if I have, let's say, 4 coins, I can have a head, head, tail, tail, head, tail, head, tail. I could have head, tail, tail, head. I could have tail, tail, head, head. Is that all of them? No, there's probably another one. Tail, head, tail, head. That might be all of them. Let me double check. No, there's one more still. Yeah. So if I want to achieve half heads and half tails, flipping some coins, if I just have 2 coins, if I just have 2, right? It's much simpler with just 2 coins. I can have first one heads, second one tails, or the first one tails, second one heads. So that's slightly disorderly or random, but compared to 4 coins, that's way orderly, right? Because if I have 4 coins, if I'm flipping 4 different coins, there's like 6 different ways. I could have half heads, half tails. I can have the first 2 heads, then the second 2 tails. After that, I can have it all these other different combinations. So something like this with 4 coins to play with, trying to get half heads and half tails, this is much more random. There's way more possible outcomes. And since there's way more possible outcomes here, I would say, just trying to, it's kind of hard to see this now. This one, here, let me erase this real quick. The entropy is pretty low for 2 coins, but the entropy is pretty high for 4 coins, right? And if I have 10 coins, it's going to be even more entropy, right? If I have 100 coins and I want to get half heads, half tails, so 50 of each, there's going to be a way more different combinations I can get to get half of each. So the more coins you have, the more disorderly it's going to be. Kind of like when it comes to these substances, right? Like liquid water versus gas water, water vapor. If the water is a vapor, it's at a higher temperature already, so it's moving faster. So having water vapor is more, there's more entropy in that phase of matter for water, because there's so many different possible ways you can have water vapor in like a container, for example. You can have the water molecules over here, over there, because they maximize, they spread out as much as possible, and they're moving pretty quickly, right? So they're bumping against each other and hitting against the walls of their container. So it's much more entropy compared to having a container of just an ice cube, right? Just an ice cube and assuming that it stays at that temperature, so it's not going to melt, assuming it stays frozen, right? There's just a bunch of water molecules stuck together in the form of a solid. They're vibrating, they're shaking, but they're not like moving all over the place and bouncing around each other and stuff like that, right? So delta S is just entropy, right? More disorder, more randomness, more possible outcomes, possibilities means positive, positive S, positive entropy. More order is negative S. So I also think about something like a collection of gumballs. I think I mentioned this in my notes too. If I have a collection of gumballs, they're all different colors of the rainbow, like red, blue, whatever, like all those different colors. And if I'm constantly bumping into the gumball container, like maybe it's at the edge of a table somewhere. If I'm constantly bumping into it, it's more likely that it's going to be random. It's more likely that if I'm constantly bumping into this container of gumballs, that they're just going to get really mixed up with each other. So the point here is that positive entropy, more disorder, let me just type this out, more disorder is also something that happens more spontaneously, Right, so if you think about that example, with a collection of gumballs on like the edge of a table, if I'm constantly bumping into it, assuming that it stays there and doesn't break or anything like that, if I'm constantly bumping into it, they're just gonna get more and more mixed up. It's extremely unlikely that you're gonna get something like this, like all the reds together, all the oranges together, all the yellows together, the blues, like all order it up. Or even like if I do bump into it and it falls off the table, if I have a bowl of gumballs and it falls off the table, they're going to get pretty mixed up on the ground. So more disorderly states, more high amounts of possible outcomes, that's just something that's more spontaneous in general. If I accidentally bump into the bowl of gumballs and it falls on the ground, it's very unlikely that all the red's going to be in this corner, all the orange is going to be here, all the yellow. It's not impossible, but it's almost impossible. It's extremely unlikely. So someone wants to look at 13. I did 2 first. First equation, for a second. 13. I'll look at 13 in a second. So if you have to find the entropy of 2 of the exact same substance, so just look at which is in. Yeah, so if it's the exact same substance and it's in the exact same state, so like 5 grams of water, like liquid water, right? 5 grams of liquid water here and 5 grams of liquid water there. Yes, if it's at a higher temperature, exactly, it'd be more entropy. It would have more entropy. Or in a container with a higher volume. So when you say higher volume, I'm guessing you kind of mean just more of that substance, maybe more mass. Yeah, so if it's the same substance, and same phase of matter, the one at the higher temperature or higher pressure or more mass would have positive entropy, would have more disorder. So if it's the exact same substance, like liquid water, exact same compound, exact same phase of matter, if one of them's at a higher temperature, it's more entropy, or if one of them has more pressure on it, that's also more entropy because they're bouncing around more, they're having more collisions among each other. Or if one of them is just more, maybe there's only 5 grams of liquid water here, but there's like 200 grams of liquid water here, the one of 200 is going to be more entropy because there's just much more water molecules that interact with each other and kind of move around each other. So yeah, that's exactly it. So someone's asking about 13. 13, yeah, what Ryan said is correct. Exactly. So yeah, Bushra, what you asked about 13, what Ryan commented, that's exactly it. So you multiply the first one by 2, and then you multiply the second one by -1. Let me know if that doesn't make sense. But yeah, thank you, Ryan. That's exactly what you do. Yeah, no problem, John. Just let me know if you guys have any more questions about entropy. Entropy can get kind of confusing. I hope the gumball and coin analogies are kind of helpful, sort of. It gets kind of complicated kind of describing it sometimes, but sometimes it helps to kind of think of things that aren't necessarily chemical reactions, but just more disorder in general. And the last video of the notes I have, the very last video, if you haven't checked it out, maybe just check it out sometime. It talks about why more disorder and more entropy leads us to seeing that heat flows from hot to cold. So yeah, more entropy and more disorder naturally happening is exactly why heat flows from hot to cold. That's explained in like the last video of the notes I did. It's not something you're gonna have to work out on the test. I did like a whole explanation of why with some equations. You don't have to do any of that math or anything like that. You just have to know that it proves it pretty much. Yeah, so that's the main reason why it's relevant in this unit. It's the second law of thermodynamics too. The first law being that heat's neither created nor destroyed. It just gets transferred from one place to another, kind of like conservation of mass, right? It's almost the same thing. And then the second law is all about entropy. If you have some sort of closed system where you're not adding more order into it, you're not, trying to manipulate it yourself, it's just closed and let alone, entropy or disorder is naturally going to happen, right? So it's kind of like having an ice cube here out in the open. If I have an ice cube right here in my hand, although my hand's touching it, so it's a little bit different. But to keep an ice cube in an orderly state, you have to add extra order from the outside. You have to use electricity, right, electrical energy to keep it frozen at a low temperature. Otherwise, it'll naturally, spontaneously start to get more disorderly. It'll melt and become a liquid. Yeah, so let me know if you need more help with enthalpy, which is H, and entropy, which is S. So it's easy to get them mixed up because they sound the same. I'll just type it here in case someone forgets. H is enthalpy, S is entropy. So number 9, I'm guessing it's letter A. Let me see, number 9. So which one has greater entropy? It's actually B, if it's smashed. Because if you have an egg in the shell, if you have an egg just unbroken, just whole in its shell, there's really only one way you can have it fixed like that and completely whole. But if you break the egg, right, there's so many different ways you can break it. You can do a natural clean break against the side of a pot like you're going to cook something, or you could try to do that and totally mess it up and get all the shells all broken up and into the recipe in the pot. You can throw it on the ground. It can get completely smashed and flattened. There's so many different ways you can break an egg. The egg can get broken like a small corner. It can get broken clean in half or down the middle. S is more entropy, so more disorder, so more possible outcomes. So yeah, like positive S is more disorder and more possible outcomes. So there's so many different ways to break an egg, right? You can like somehow completely cut it cleanly in half. I don't know how you could, but you theoretically, I guess, could. You can break it in like the small corner. You can completely smash it flat. There, you can do so many different things to break it. But an egg completely all together as one whole unit, it's only in that state one way, just as it came out of the chicken, basically, right? You can't really put it back together in that way, if that kind of makes sense. There's only one way to get the whole egg. Yeah, S is entropy. S is entropy. So positive S is more entropy. It's like that comment I just said. So positive S is more disorder, so more possible outcomes, so high entropy. Yeah, S is entropy, H is enthalpy. So for number 11, how do you set up the equations that you add together? 11. Oh, so 11 here. Let me see if I can just show it to you guys. I actually typed it out a second ago. It's one where you go through multiple different phases of matter. So you have like 3 heat equations to work with. Here, one second. I'm on a different page right now. You have like 3 heat equations to work with, and you have to add them all together. Let me just... I don't know why I have these headphones on. I can't really, it's like I can hear anything you guys are saying anyways. Oh, that didn't show up well. Sure, I'll have to type it out. So for that one, you get, I'm just gonna put M for the mass, so it's the same mass, right? So it's first at what, 137 degrees? 137. So the first delta is 137 minus 100. And then here I'm gonna type a couple things. And then it's going through the phase change. So there's a couple things I'm going to type up here. So the second one is just the ML. That's the Q equals ML equation for just the phase change, right? So that number 2260, that's the latent heat of vaporization. So I don't know, maybe this does help. That's the latent heat for vaporization. So that's something that would be given to you on the test. The third and final one is when it's a liquid. So that's when you use 4.184. And then the delta temperature is 100 minus, what is it, 80, 45. 100 minus 45. Then you add all 3 Q's together. So you do the first heat equation from the highest temperature, 137, to 100. You have to stop at 100 because that's the temperature that water boils or condenses at, right? So 100 is the temp for water boiling or condensing. I spelled condensing wrong, but condensing. Right, so 100 degrees is the temperature for water to boil to condense. So that's why you have to use that as kind of like the middle temperature. So the first heat equation, it's 137 minus 100, but that 2.01, that's the heat capacity for water vapor. That would be given to you guys. That's just the C for water vapor. For Q2, it's the short equation, ml, because that's just the phase change. So you just have the mass times 2,260, because that's the latent heat for vaporization of water. Again, that would be given to you guys. And then for Q3, you use that much more familiar 4.184 as your C. That's the heat capacity for liquid water, right? 4.184. But the change in temperature there is 100 minus 45. Because 45 is that lowest temperature. And again, because it's condensing down from being a gas. So 100 is that middle temperature. I know sometimes I think people get confused because since it's cooling down in this problem, right? It's going from a high temperature to a low temperature. It's not really like I'm doing final minus initial there per se. You could do final minus initial, but it'll be negative, and you just want to take the absolute value. So for number, what is this one? Number 11, you're just trying to find the total magnitude of the heat needed to cool this water down. If this was like a problem on the test, just so that wouldn't be an issue, I would just make sure it'd be something that's heating up instead of cooling down. Yeah, let me know if you have any other questions about that, Karine, because those ones are just kind of a little bit longer. It's like usually 3 equations. If it was going through 3 phases from like gas to liquid to solid, then there'd be 5 equations, but I don't think I'd give you guys that anyways. It's just kind of long. But yeah, so let me know if you need me to tell you what any of those numbers are again or why I did them. But yeah, Bushra, S is entropy. So positive S is more spontaneous, and more disorderly, more possibilities. And negative S is more orderly. S is entropy. Well, yeah, let me know if you guys have any other questions about the study guide at all. And I'll put up the solutions to the study guide on Thursday too, kind of like last time. So yeah, that's really all we have for this week is just the study guide from yesterday and the test Friday. Let me see something. Yeah, you guys don't have to, but if you're interested, there is a Kahoot link to like just more practice of this stuff. Yeah, it's up to you guys. Yeah, let me know if you have any other questions at all about like the study guide or anything like that. Yeah, that's the pin. So yeah, you guys don't have to, but if you're interested in doing some more review. Number 5, I got the H5 is negative, so reference value. Number 5. Oh yeah, exactly. You're right. So for exothermic reactions, it's negative. So then the reactants have exactly, they have lower energy. Yep, you're right. Yeah, because because of the first law of thermodynamics, energy isn't created or destroyed. So it's not like the energy disappeared or anything like that. It just means the total energy in the chemical reaction from reactants to products, there was more energy being released in the formation of products than there was being absorbed to break down the reactants. So that's why it's exothermic. There's more energy being released to form the products. So yeah, you're right. It's definitely negative enthalpy, and the reactants have a lower energy. But yeah, again, the energy didn't disappear or anything like that. It's just some of that energy itself was probably within the bonds of the new products, but at the same time there was more energy being released than there was being absorbed to break apart the reactants themselves. So there was just more energy being released in the products. Yeah, let me know if you guys have any questions or anything. So for 12, let's see, for 12, it looks like for 12, we only have to multiply the first one by -1. So here, let me look at that. So for number 12, we just multiply the first, type out the first reaction by -1. So let's double check. I just want to make sure I'm okay. Yeah, okay, that looks good. So that -1 gets multiplied by that negative enthalpy value. So it was -123 kilojoules. So here I'll type it out. So we get positive 103 kilojoules plus negative 262 kilojoules, or just minus 262 kilojoules, right? So I'll type it out like this. So -1 times -123 kilojoules, so that's going to become positive, plus negative 262 kilojoules. So yeah, you're going to get 123 minus 262. So it's going to be some negative number, if that makes sense. Because we didn't do anything to the second reaction there. We just multiplied the first one by -1, so it became positive. And for 13, like Ryan said before, you multiply the first one by 2, the second one by -1. So you multiply the first by 2 and the second by -1. So you get 2 times negative 542.2. Yeah, exactly. 2 times negative 542.2. What's that negative? Yeah, it's negative. Negative 542.2. Okay, cool. And then you add -1 times what was that? Negative 571.6, negative 571.6 kilojoules. So in that case, you're going to get whatever 2 times negative 542.2 is, so some bigger negative number, but you're going to add positive 571.6 because you're multiplying it by -1, and it's already negative, so it becomes a positive. So yeah, for those Hess's law problems, your final answer is always like some number based on whatever you get there. Oh, number 2. Sorry, I must have missed that. Number 2, thanks for the heads up. So we're looking for the specific heat of the metal. So we have the mass is 30 grams, we have the change in temperature, and we see the energy being absorbed. Oh, yeah, if you're wondering about that last sentence about what metal it is, don't worry about that. But basically, you're using this equation, using that equation, right? Because it's changing temperature. So if it's not changing temperature, if it's just going through a phase change at a constant temperature, then it's Q equals ml. But in this case, it's changing temperature. So in that case, it's going to be that equation, the final minus initial. So I'm just going to plug all the values in. So we have 1 kilojoule, right? So that's 1,000 joules. 1 kilojoule is 1,000 joules, so you need it in joules. You have to convert it to joules. And we have 30 grams, times C, which is what we're trying to find, and then final temperature minus initial, so 59.2 minus 22. So you kind of set it up like that, and then just trying to get C by itself. So 59.2 times 22, or minus 22, sorry, minus 22 is 37.2 times 30. So it's basically going to be 1,000 divided by 1,116. 1,116, yeah. So that'll get you your C. Right, because 30 times 59.2 minus 22 is 1,116, yeah. So it'd be 1,000 divided by that. So I'm not sure. Don't worry about the question. It says what metal it is. I should have erased that. I forgot that that was on there. There might be a table in your guys' textbook, though, that has it. There probably is. I just haven't double checked. But you don't have to worry about that part. So yeah, let me know if you guys have any other questions, if I missed a question or anything, in case I missed one. Yeah, no problem. Just let me know if you guys need any other help or anything. I have that Kahoot thing going too if you guys are interested. You don't have to, but it's just up there because I know last time I think a couple people said they were interested in doing that, but well, we don't have to. Yeah, so let me know if you guys want to look at any other examples, if you have any other questions at all. Yeah, let me know if you guys have any other questions or anything like that. If you want to go over any other concepts or anything. Yeah, number three is, I believe, the heat equation that is just a phase change. There's a constant temperature, right? So we're just using this equation when there's a phase change, there's Q equals ml, right? But this one over here, one second, is 4. So the second one that I typed out, that's when it's at one particular phase, and it is changing temperature. So the first one, Q equals ml, is the one we're going to use because it's just going through a phase change. There's just 15 grams of water, right? 15 grams. And the L is the latent heat of fusion in this case. But just going to be that. So it's a bit easier and quicker, just multiplying. You don't have to do any subtraction or anything like that. But the longer ones, like the one that I think Kareen asked about, number 11, yeah, number 11, I believe it was. That one, it's changing temperature and it's going through a phase change. So that's why you have like the two changing temperature equations, and then you have that one Q equals ml equation as well. You have like three different ones to work out. But yeah, for the one you asked about, number three, it's just 15 times 334. It's just straight up multiplication like that. Yeah, so if it's changing temperature and going through a phase change, then you have two of those MC delta T equations and one ML. But if it's just a phase change, then it's just ML. And if it's at that constant temperature, it's just going from maybe liquid to gas or solid to liquid or something, then it's just ML. Yeah, I know I'm supposed to just now officially only be scheduled to have office hour live streams like this, just Tuesday between 1 to 3 and Friday between 11 to 12. But I'll try to see if I can do something on Thursday too, just to not to force anyone or anything. I mean, these are open anyways. No one's forced to come to these, but I'll do something on Thursday too, just because our test is Friday, just in case anyone wants any last minute questions. I just don't want to step on any other teacher's toes or whatever. So, excuse me. It's a device that's meant to um, insulate whatever reaction is going on inside of it. So it's used to determine the heat that's being transferred within a chemical reaction, um, but it does so without any heat being lost to the surroundings, to the environment. So it's basically like an insulated container meant to measure the heat that gets used in a reaction. So the key part, because some people on the quiz didn't add that insulation part. They didn't add the fact that there's no heat lost to the environment or there's no heat coming from the environment, from the surroundings. So they might have just said it's a device used to measure heat and reaction, and I might have said that's not enough description because I was just wanting to look for that part about no interaction from the surroundings. So no heat leaving to the surroundings, no heat coming from the surroundings. So it's insulated. So it's kind of like, I mean, this isn't as insulated as I like it to be. Sometimes I feel like it actually doesn't stay super cool, unfortunately. But um, it's supposed to be insulated, right? This hydro flask. So if I had some sort of reaction going on in here, and I had a thermometer within here, because the way they do it is they basically have like, if we had a lab of this stuff in class, we would actually just use coffee cups. Coffee cups are pretty good approximators for calorimeters. We just take two coffee cups, like the styrofoam coffee cups, stack them on top of each other, two of them, and then you usually have some sort of like cork lid, some sort of like very like tightly packed lid of like cork or other styrofoam, and you have a little thermometer just kind of sticking through it, so you can measure the temperature difference. While the heat should mostly be contained within the styrofoam cups, it shouldn't be leaving, and you shouldn't have any heat coming into the styrofoam cup if you're like in a super hot place or something. So yeah, it's basically a device used to measure the heat involved with a chemical reaction without any heat loss to the surroundings or heat gained from the surroundings. So you can just say it's insulated. Oh, no, no, no. Yeah, let me know if you guys have any other questions or anything. Yeah, they're not saying that it's going to happen, um, but it's, I guess, something that was made in the governor's speech recently, that he just kind of thinking about that as a possibility, because of the obvious sort of a gap in knowledge that's going to inevitably end up happening with the fact that we're, having to learn from home and stuff like that, and learn virtually. And a lot of you guys that have been in this chat have been doing a great job at still learning and doing a great job and staying on top of things. But there's other students who maybe don't have access to internet or don't have access to certain things, and they or there's even some students just do have access but just haven't done anything, and so they're not going to be as prepared for chemistry. It's not as detrimental depending on what you want to go into. If you're not even planning on going into science, for example, but you just want to go to a Cal State or a four-year university, you take chemistry. um, but if you're not going to plan on going into science, you're not that much at a disadvantage. But for other classes, like especially English or math or foreign language, this little gap in time right here since March 13th, especially if you haven't done any work at all, if you kind of just blown things off, there's going to be like a gap in knowledge for sure. So, yeah, the governor's not saying that that's going to happen, but it's just a potentiality. That's something I think he's just kind of chewing on, something he's thinking about. So, hopefully not, because it'd be kind of strange, kind of different. I mean, we'll see what happens, but yeah, that would make things kind of complicated because at July, because even some summer school programs are still going to be going into July. I'm supposed to be working summer school, and that's ends like middle of July. So if we start school in July, that kind of mess everything up. Be kind of strange. So I'm not sure if that's actually going to happen, but it's just something he was talking about. So we'll see. Yeah, let me know if you guys have any other questions at all. Looks like maybe no one wanted to join Kahoots, but that's okay. Um, it's there in case anyone does want to. So here, I'll go ahead and yeah, so we'll see if it happens, but hopefully it's not as crazy as that. I'll be right back. Let me know if you guys have any other questions. So yes, let me know if you guys have any other questions about anything. And yes, let me know if you guys have any questions about anything. All right. If you guys don't have any other questions, I might take off. I know I'm only supposed to technically from now on have these live streams. I guess Tuesday from 1 to 3, anywhere in between that time, and Friday between 11 to 12. I'll try to still do something on Thursday this week, just because our test is Friday. So if you guys are able to, if you're free, I'll try to do something on Thursday if you guys are interested. But I'll probably take off though. Just let me know if you have any quick last minute questions or anything like that. All right, take it easy, Ryan. Have a good one. See you guys later.